Rasul, and I'll be going over the Physics 2211 Lab 4. This is over the motion of a spring or of a mass at the end of a spring. So first we were giving a video of a spring or a mass with a spring attached to it. In the video, the mass is moving in a circular motion. We were told to replicate this in GlowScript and analyze this and its movement in Tracker. So after putting it into Tracker, we refined the x and the y coordinates of our mass as it moved at the end of the spring. We put this data into a CSV file so that we could feed it into our computational model. And here on the side is a list of the coordinates shown. On the left is the x values, and on the right is the y values. So as you can see, the x values are moving up and then moving down, and same with the y values, but we'll talk about this later. So for our computational model, first we had to edit the variables responsible for our calculations to match the data we got from the video analysis. These concern the spring's activity in the model. So as we edited the L with the ball position minus spring position, L hat, and S to be L over the magnitude of L, and the magnitude of L minus the relaxed position. Then we were able to find the kinetic energy, gravitational, and surface and total energy. All right, furthermore, we put these into the calculation loop. We add the gravity force, spring force, edit the position and the velocity of the ball, add the energy changes using the kinetic equation and the respective gravitational surface potential energy equations. So first we did the F-grav, and this is uh, negative ball mass times gravity, and then F spring, F net with our grav plus F spring, which is found by our negative spring tension times S times L hat. Our ball velocity and ball position update formulas using Newton's second law, and then again our update for our spring position. These are all in the calculation loop, so these are in the while loop and updating every time that we're ticking in the computational model. Then we did the spring axis, and again, our kinetic and delta K, gravitational and surface potential energy equations with the deltas, which is what we calculated minus the initial, and then our total energy and our delta total energy. So our final results is that our computational model reflects the motion of the mass from the video, and the spring accurately follows this mass. Um, and as this red ball oscillates, the spring follows. Below the view of the model, you can see the chart showing change in energy versus time, and we will talk about this later, but you can see here that our delta E is a straight line. So talking about that, our first what if question is for your model system, is the energy principle satisfied? We can see that it is, because as our U gravity and our U spring oscillate in opposite patterns, they keep the delta E straight. So it zeroes out and the energy principle is satisfied. Secondly, we can see these oscillating motions in opposite in the X and the Y tracking. So the second what if question is to make two separate estimates of the oscillation periods, compare the two estimates, and discuss. From the data in Tracker, we can see that both the position of X and Y oscillate in 1.5 second intervals. So this first point is at 1.5 seconds, and the second one is at 3 seconds. And then this first point here for the Y is at 0.665 seconds, and this is at around 2.2. So we have a 1.5 difference and a 1.6 second difference, and these continue through the rest. So they're alternating in the same period, but following opposite patterns. So concluding this, we know that using Tracker, we were able to find and take data from the video and create a computational model. This model lets us graph and observe the changes in energy over time, where we can see the energy principle being satisfied. This is one of the ways that we can tell that the model is accurate. Using this data, it also shows us that the period of time between oscillations for X and Y are the same, but they move in opposite patterns. That concludes, and thank you.